Today we're tackling something truly mind-bending, the latest physics Nobel Prize.
Yeah, it was awarded for discovering macroscopic quantum mechanical tunneling. Sounds complicated, right?
It really does.
Mm-hmm.
But our mission here is to unpack it because this science is basically the bedrock for the quantum computing revolution that's, happening right now.
Absolutely. And the prize itself, 11 million Swedish kroner, went to 3 scientists, John Clark, Michel Devoret, and John Martinis.
And, one of the winners, Professor Clark, his reaction was just golden. He said it was the surprise of my life.
Completely stunned, I think he said.
Yeah, which really makes you think, doesn't it? Decades of work, and then bam, it changes everything.
It does, and the Nobel Committee often points this out. All our tech, like your phone, the internet cables.
It all runs on quantum mechanics already in a way.
Exactly. But this discovery is different. It's about showing those weird quantum rules don't just apply to single atoms.
Right, they can actually govern things big enough for us to build and control. That's the macroscopic bit.
Precisely. So the full citation, it mentions 2 key things.
Let me see. Discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. Okay, 2 big ideas there.
Let's take tunneling first. That's the one people might have heard of. The idea that a particle can, pop straight through a barrier.
Yeah, the classic analogy is a ball going through a solid wall, even if it doesn't have the energy to go over it. Super weird.
Totally weird. And we knew that happened with atoms, based on theory from way back. But the breakthrough here...
Wasn't just seeing tunneling.
No. It was proving that a whole collection of particles, millions of electrons moving together in a superconductor,
Could act like one single quantum thing.
yes, that was the mind blower.
Yeah.
A macroscopic quantum object.
Okay, so that connects to the second part then, the energy quantization.
Exactly. See, in a normal circuit, energy flows smoothly, continuously.
Like turning a dimmer switch.
Right. But they showed in their special superconducting circuit, the energy wasn't continuous. It jumped between specific, discrete levels, like steps.
And those steps, those discrete levels, that's the hallmark of quantum mechanics.
That's it. It proved the whole circuit was playing by quantum rules.
So how do they actually do it? How do they build this quantum circuit?
The key piece of hardware was something called a Josephson junction.
Oh.
Basically, it's 2 superconductors separated by a really, really thin insulating layer, like a tiny sandwich.
An insulator should block things, right? Classically speaking.
Classically, yes. But they found the whole quantum state of the circuit could actually tunnel across that thin barrier.
The whole thing just jumps across.
In a quantum sense, yes. And it created a voltage they could measure. But here's the really cool part.
Go on.
They timed how long the system would stay on one side before tunneling. And that timing, it wasn't predictable moment to moment, but statistically.
It followed probabilities.
Exactly the same probability rules as, say, radioactive decay. Pure quantum statistics, but in a man-made circuit.
Okay, but wait. If it's all based on probability and chance, how do you build something reliable, like a computer, out of that? Seems kind of shaky.
Well, it's about controlling those probabilities.
Oh, yeah.
Because they proved the energy levels were quantized, distinct steps, and the tunneling followed predictable statistical rules.
They showed they could handle the system, control its quantum state.
That's the leap. They demonstrated control over a macroscopic quantum system. And that control, that ability to manipulate these states, that's what quantum computing needs.
So this directly led to the building blocks of quantum computers.
It laid the essential groundwork, yeah. Especially for what we now call superconducting qubits. They're one of the main ways people are trying to build these machines today.
And you can see the direct line, right? John Martinis, one of the laureates.
Google hired him back in 2014.
To do exactly this. To take this fundamental physics and build a working quantum computer.
It's pretty amazing. You've got this quantum theory that's, a century old?
Still throwing up surprises.
Right. But it's also the quiet foundation of literally all the digital stuff we use every single day.
So think about that for a second. The same basic physics, the quantum rules inside the chips in your phone right now. That same physics is now being deliberately engineered, harnessed to create computers that could potentially solve problems we can't even imagine tackling today.
It really is a dual reality. Quantum mechanics gave us the digital age we live in.
And now it's poised to define whatever comes next. The foundation of the past and absolutely the engine of the future.